Okay, so what you see here is the beginnings of what's called the Fibonacci sequence, which is really cool in itself. You can go to YouTube, Google videos about that, but that's not quite what we're doing here. The idea behind the Fibonacci is that each value is just the sum of the previous two values. So 5 would be the sum of 2 and 3, 13 would be the sum of 5 and 8. If we wanted to get the next value, we would add 8 plus 13, and that would give us 21. If we would want the next value, 13 plus 21 would give us 34, and so on. So the question is, can we write a function for the Fibonacci sequence? And what I mean here is the nth Fibonacci number. So we could say that this is the first Fibonacci number, the second Fibonacci number, and so if we want the nth Fibonacci number, how could we get that? How could we get, this is the 1, 2, 3, 4, 5, 6, the seventh Fibonacci number? Well, as it's defined, it's just the sum of the previous two Fibonacci numbers. So it'd be so nice if we could just return Fibo of n minus 1, the one right before it, plus Fibo of n minus 2. So to get any Fibonacci number, we would just get the Fibonacci numbers, the two numbers that were right before it, and then add it together. So let's run this and see what happens. Okay, so far, you might wonder, why didn't anything happen? Well, all we've done is put a function into our space here. So we need to call that function. So let's maybe call Fibo of 5. So this should give us 1, 2, 3, 4, which turns out to be 5 itself. And we get maximum recursion death exceeds. So what's happening here? Well, because we're calling the function itself, in order to find Fibo n minus 1, it has to call call itself, and then it needs to know Fibo n minus 2 plus Fibo n minus 3. But to get Fibo n minus 2, it calls itself, and it has to get Fibo n minus 3. And it keeps on going deeper and deeper. It doesn't have an end. So we need to give it a little bit of help. We might say something like, if n equals 1 or n equals 2, return 1. So what we're saying there, if we're looking for Fibo of 1, return 1. And if we're looking for Fibo 2, return 1. This way it does have an end point. So the recursion isn't going to go on infinitely long. When we go try to get Fibo of, say, 3, Fibo of 3, well, n does not equal 1 or 2. N equals 3 for Fibo of 3. But it would return Fibo of 2 plus Fibo of 1. And Fibo of 2, that's easy enough because n does equal 2, so that's just 1. Fibo of 1 is easy enough also because n does equal 1, and so that's 1. So that would be 1 plus 1, and it would return 3. So if we were trying to find Fibonacci 3, this would work quite nicely. So let's take a look again here. And now let's call Fibo of 3. So that gives us 2. And if we go to Fibo of 5, that gives us 5, as we had hoped. And let's go a little bit bigger up on our list here, Fibo of 8. And we do get the 8th Fibonacci number, which is 21. So it might be helpful to put a print statement in here to try to figure out what's going on here. So maybe we'll just basically see how many times the Fibonacci function is being called here. So every time it gets called, we'll print the number that it's being called on. So take a look at this. And now let's try Fibo 3. So notice that it's calling on Fibo 3, but in order to get that, it has to solve Fibo 2 plus Fibo 1, and that's why it's calling these other functions here. If we do Fibo 8, notice how many things get called. In order to get 8, it has to get 7. In order to get 7, it has to get 6, all the way down to 1. Once it does get 2 and 1, then it can get an answer for Fib03. And then we start coming back these, we've kind of crawled deep into a cave and we're coming back there. So this turns out to get quite tricky fairly quickly. If we try Fibo of 20, that's okay. Fibo of 30, there was a pause there. Fibo of 40, we're really not that high yet. The 40th Fibonacci number is something you could calculate with hand, maybe a little calculator or something, but already Python's struggling because of how many different calculations it's doing. Remember, we saw how many calculations it did just for Fibo of 8, but this is now increasing exponentially. It's blowing up in terms of the number of calculations that it's doing. It will, I think, I haven't tried this on my computer. There we go. We did eventually get the 40th number. Now, if I would try Fibo 50, we would be waiting a long, long time, perhaps hours to get Fibo 50. So how do we avoid the situation where we're waiting forever? Well, there's something called a cache, or memoization, not with the R, memoization. And the way it works, it's like a dictionary, which we'll learn about more thoroughly very soon. But the way the cache works is we put in each Fibonacci number, so maybe the first Fibonacci number is 1, the second Fibonacci is 1, and we could keep going, but we're going to let the program fill in the Fibonacci for us. The problem here is when we get to, say, Fibo 5, we're calculating that hundreds and hundreds of times when we're up at a high number because of all the different ways that it's going down and calling itself. So if we could just get it once and then save it, that would be perfect. So we can say something like, if n in cache. So basically, if we've already calculated it, whether it's Fibo 5 or Fibo 20, whatever it is, if we've already calculated it, let's go inside the dictionary and find the key or the value that's associated with that particular number. So Fibo 5, cache of 5 would just be 5. Cache of 6 would be 8. Cache of 7 would be 13, and so on. If it's not in cache, then let's say we'll put it in the cache. Okay, and then we can return. We could leave what's there, or we could return it. So basically, if we already find it in our collection, in our storage container, we'll just return what the value is directly. If it's not there, let's go ahead and calculate it, and then we'll return what the value is. So this, notice Fibo 40, we get that pretty quickly. Fibo 50, no problem. Fibo 100, we can start to get pretty crazy here. Fibo 500. I mean, these numbers would take years and years if we were to do it with our original program. So we're now getting into, now if we went high enough, I think, let's see, oops. It is possible to exceed the recursion depth. So our program's fast enough to handle this, but the problem is you can only go down about 1,000 times, and then that's called the maximum recursion depth. After that, it's saying, okay, you're probably not doing what you want to do here. Now you have two options. One is you could change the maximum recursion depth. If you're sure you know what you're doing, you can allow your recursions to go much deeper, call the function to call itself many more times. Or you can build to it. So if we just slowly build up to that value that we were looking at, then notice we don't have to go in recursion, we don't have to go to a depth of 2500 because we already have the first 2000 values in our cache. So we really only have to go down 500 levels until we start hitting values already stored in our cache. And now we can do our Fibo 3000. So this is the power of recursion and a cache together, memoization with recursion. The two combined is a type of programming called dynamic programming. And it's an advanced programming. You'll see it on some of the really high-level Checkio problems. Uh, you'll see it mentioned in various Stack Overflow boards, but dynamic programming, this is one way of doing dynamic programming if you can do recursion, but remember everything that you've done so far so you don't have to keep repeating it over and over again.